I wish you the best of luck on solving those open problems, and I encourage you all to submit for next year and to exceed Manfred's $600 threshold. So we haven't reached it yet. Thanks.
Okay. Hi, everyone, and welcome to the session on privacy and robustness. And friends, our first talk, do we have the first speaker? Yes, please come. Is Akshay Degvekar.
Okay. Can you all hear me? Okay, good. So thank you for the intro. I'm Akshay Degvekar. Today I'll be talking about computational limitations in robust classification and win-win results. This is joint work with Preetam Nakiran and Vinod Vaikunthanathan. Okay, so let's start. So modern machine learning is used everywhere, and as its use increases, some security questions related to machine learning are coming to surface. And today we'll be talking about one of them, which is that of adversarial perturbations. So let me start by telling you what those are. Okay, so an adversarial perturbation roughly takes the following form, that you start with an image and add a small amount of imperceptible noise. It's not random, but it's a very small amount of noise. It leaves the image unchanged, but it dramatically changes the output state-of-the-art classifier would give on this input. And so we want, this is not great because we would ideally want our classifiers to behave similar to our eyes. And we want to understand that why do these adversarial perturbations arise and build classifiers which are robust to such perturbations. And so there's a very large body of work surrounding this question, and I won't really have time to go into it. Today, we would focus on seeing how this question interacts with computational bottlenecks. That is it when do robust classifiers exist? If they exist, can we learn them? And can we learn them efficiently? So this question was first considered by Bubeck, Lee, Price, and Rosenstein. And they postulated that we have a hierarchy of worlds in which a classification task could lie, each one more optimistic than the previous one. So the most pessimistic you could be is to say that no robust classifier exists for such a classification task. So when I say a classifier is robust, I mean that such a small perturbation shouldn't affect the output of the classification. I'll define it formally in a bit. Okay. So the first thing you could assume is no robust classifier exists, in which case we are kind of doomed. You could have better scenarios. For example, it could be that robust classifiers exist, but efficient robust classifiers don't. And so today, when we say efficient, we would focus on polynomial time algorithms. You could make other choices, but that's what we would do. Okay. The next possibility is that you could have efficient robust classifiers, but they need too much training data to learn. So if you have a learning algorithm, it needs a lot of data to even information theoretically figure out what the classifier is. We could have other scenarios. So it is possible to learn such a classifier, but even with small amount of training data, but a learning algorithm which does so takes a lot of computational resources. And finally, which is somehow the most rosiest scenario, is that these classifiers exist, they are learnable, we just haven't found out the right algorithm yet. And okay, so good. So let me first talk about our results, and then I'll compare it to prior work. And so what we do is that we show that under cryptographic assumptions, various of these properties can be realized. So in particular, we show three things. So first of all, we show that if we show classifiers where inefficient robust classifiers do exist, but no efficient classifiers do. We also show new classification tasks where efficient robust classifiers exist, but they are unlearnable. And I'll compare it later. And finally, we show cryptographic consequences of such results. That is, we want to understand for which tasks are such classifiers a reality. And we would show that the existence of such tasks implies crypto. And so I'll discuss what that is later. Okay, so now I'll go into our results in a bit more detail. And so for this task, let me quickly summarize the notation. So we have two distributions over a binary alphabet. And a classifier's goal is to get, when it gets a sample from one of the distributions, it has to tell which of the two distributions it is. And a robust classifier has a more difficult job, which is that for not only the original sample drawn from the distribution, but also for points which are close to it. And so in this talk, we would focus on Hamming distance. So for any point which is close to this point, you have to give the same answer. And you have to do this so for most points with good probability. And we can consider it in other norms, but today, binary. OK, so let me tell you about the first result, which is that a world where robust classifiers exist, but efficient robust classifiers do not. So we show that assuming one-way functions, which is pretty much the minimal cryptographic assumption you could assume, there is a learning task where normal classification is very easy. Robust classification is possible inefficiently to a large degree. That is, you could perturb a constant fraction of the input, and you'll still be able to classify. But no efficient robust classifier exists. That is, I can perturb one bit of the output such that no efficient classifier is able to classify these correctly in a robust sense. Okay. The second result we show is in this world of learning robust classifiers. So BPLR showed two results in this world. So one, they showed classification tasks in the SQ model, where efficient robust classifiers exist, but learning them takes exponential time. So for those of you who don't know SQ, it's basically a restricted form of computation where you don't, which is where you are only allowed a certain form of learning queries. The other thing they showed was that assuming factoring, a cryptographic assumption, you have a classification tasks such that an efficient robust classifier exists which can perturb a constant number of bits, but learning one which protects against even one bit tampering is hard. So we improve on this in two regards. So we improve the assumption, which is we show that under a weaker assumption, which is that one-way functions exist, you have an efficient classifier which can tolerate a linear number of corruptions, but learning even a non-trivial robust classifier is hard. That is learning something which protects against even one-bit adversaries. Okay, and finally, let me talk a bit about the cryptographic consequences. So here we show what we would call a win-win result. That is, we show the following, that what kind of tasks can exhibit this behavior, that they have robust classifiers, but they are hard to learn. And we show two things, that for any classification task where efficient robust classifiers exist, either we can learn them efficiently, or we can construct crypto out of them. So we can construct one-way functions, and hence symmetric key cryptography, and more. Okay, so what does this mean for image classification, right? So we would strike a note of cautious optimism. So cryptographic assumptions are very hard to find in the wild. And now you are in this very scenario where we would believe that an efficient robust classifier exists, that is RIs. And so then either we can learn them, or we would get crypto. And crypto is probably hard to get from image classification. Okay, so with that, I'll summarize. So we show two things. We show that under minimal cryptographic assumptions, there are classification tasks where efficient robust classifiers don't exist, and tasks where they do exist, but they are hard to learn. And we show a win-win result, which is that for classification tasks where efficient robust classifiers do exist, either we can learn them, or we can derive crypto out of such tasks. Okay, with that, I'll stop. Thank you.
Thank the speaker again. Our second talk is by Omar Montasser, and this is one of the winners of the Best Student Paper Award. So let's join me in congratulating the author.
Hi. This is joint work with Steve Haneke and my advisor, Nati Srivrao. So we study a basic question, which is how can we learn predictors that are robust to adversarial perturbations at test time? So the setup is as follows. We have an instance space X. Think of this as a space of images, and we have two labels, plus and minus. We want to be robust to an adversary U that can change a point X in the space to a perturbation in the set U of X. And this happens at test time. So there are multiple, we can think of a few examples of adversaries. It could be an L infinity ball around X with some radius, or an L2 ball, or maybe just some arbitrary set. And now with this adversary in mind, our main object of interest is the robust risk. The robust risk is defined as for a predictor H with respect to a distribution D, is defined as the probability over samples X and Y drawn from the distribution that there exists a perturbation where in the set U of X, where the classifier H labels the perturbation differently. So in other words, a predictor H is robustly correct if and only if it labels every point Z in the set with the label Y. So now given a class of functions H with predictors that map from X to Y, we want to know whether it's possible to learn from a finite sample a predictor H that competes with the best robust predictor in the class. More formally, a class H is agnostically